In this module, you will learn about minimum velocity of a particle to move in a vertical circle. Take a small bucket of water and rotate it slowly in a vertical circle. What do you think will happen? The water in the bucket spills out as it reaches the highest position along the vertical circle and becomes upside down. Now, do it again, but rotate the bucket quickly. This time, the water in the bucket does not spill out even when the bucket is upside down at the highest position along the vertical circle. Why doesn't the water fall out of the bucket when it is rotated fast? The water does not spill out as the centrifugal force on the water inside the bucket is more than the weight of the water. However, the centrifugal force will be more than the weight of the water only above a certain minimum velocity. Let's see what minimum velocity is. Consider a particle of mass m is suspended from a fixed point O by a massless, inextensible string. It is imparted initial velocity v1 in the horizontal direction. If v1 is greater than the critical velocity, then the particle starts moving in a vertical circular path. To know the critical velocity and basic characteristics of motion in a vertical circle, consider any instantaneous position of the particle. Let the instantaneous position of the particle be L. At this position, the string makes an angle theta with the vertical line OP. The two forces that act on the particle of mass m at point L are the particle's weight mg, which acts vertically downwards, and the tension in the string T, which acts along LO. Let the instantaneous velocity of the particle at point L be v. It acts along the direction of the tangent to the circle at L. We can split the weight mg into two components, mg sin theta and mg cos theta. When the particle moves along a vertical circular path, the radial acceleration acts towards the center of the circle, which is equal to v square upon r, where r is equal to the radius of the particle's circular path. The corresponding instantaneous centripetal force on the particle is equal to m into v square upon r. The tension force in the string acts on the particle towards the center of the circle. On the other hand, the force mg cos theta acts away from the center of the circle. So, the net force acting on the particle is given by T minus mg cos theta. Due to the centripetal force, the particle moves in a circular path. So, the net force acting on the particle is equal to the centripetal force. It can be written as mv square upon r is equal to T minus mg cos theta. By rewriting this equation, we get T is equal to m into v square upon r plus mg cos theta. Let this be equation 1. Let us now compare the total energy of the particles at points P and L. When the particle is at P, the height of the particle is 0 along the circular path. So, its potential energy at this point is also 0. When the particle reaches point L, the height of the particle becomes h. Hence, the potential energy at this point is equal to mgh. According to the law of conservation of energy, the total energy at P is equal to the total energy at L, that is, kinetic energy plus potential energy at P is equal to kinetic energy plus potential energy at L. It can be written as m into V1 square upon 2 plus 0 is equal to m into V square upon 2 plus mgh. On simplification, this becomes m into V1 square upon 2 is equal to m into V square upon 2 plus mgh. Let this be equation 2. Now, look at the right-angled triangle OML. Cos theta is equal to OM upon OL. We can also say that OM is equal to OL cos theta. We know that OL is equal to R, so OM is equal to R cos theta. From the figure, MP can be written as OP minus OM, where MP is equal to H and OP is equal to R. By substituting these values, we get H is equal to R of 1 minus cos theta. Let this be equation 3. From equations 2 and 3, we can say V square is equal to V1 square minus 2GR of 1 minus cos theta. Let this be equation 4. By substituting the value of V square in equation 1, we get T is equal to M multiplied by V1 square upon R minus 2mg plus 3mg cos theta. Let this be equation 5. From this equation, we can understand that tension in the string T is the function of theta. Using this equation, we can find the details of the particle at different positions along the circular path. Let us consider 3 positions of the particle: the lowest point on the circular path, the point midway along the circular path when the string is horizontal, and the highest point on the circular path. In the first case, the particle is at the lowest point P of its vertical circular path. At this point, theta is 0 degrees. Let the tension in the string be Tp. By substituting these values in equation 5, we get Tp is equal to M multiplied by V1 square upon R plus mg. Let this be equation 6. In the second case, the particle is midway, which means that the string is briefly in the horizontal position. Let the position of the particle be q and the instantaneous velocity of the particle be v2. At this point, theta is equal to 90 degrees. Let the tension in the string be Tq. By substituting these values in equation 5, we get Tq is equal to M into V1 square upon R minus 2mg. Let this equation be 7. When the particle moves from P to Q, the change in the tension can be written as Tp minus Tq. Substituting the values of Tp and Tq from equations 6 and 7 and then solving the equation, we get Tp minus Tq is equal to 3 mg. In the third case, the particle is at the highest point along the circular path. Let the position of the particle be r and the instantaneous velocity at this point be v3. At this point, theta is equal to 180 degrees. Let the tension in the string be Tr. By substituting these values in equation 5, we get Tr is equal to m into v1 square upon r minus 5 mg. Let this be equation 8. When the particle moves from P to R, the change in the tension can be written as Tp minus Tr. Substituting the values of Tp and Tr from equations 6 and 8 and then solving the equation, we get Tp minus Tr is equal to 6 mg. Based on the values of Tp minus Tq and Tp minus Tr, we can say that the tension in the string decreases as the particle moves from the lowest point to the highest point along the vertical circular path. The tension in the string is maximum when the particle is at its lowest point P, but minimum when the particle is at its highest point R. In equation 8, the values of mass m, radius r and g are constant for a particle. So, the value of Tr depends only on the velocity of the particle v1. Based on the value of v1, Tr can be positive, negative or 0. If Tr is a negative number, then the string would become slack and the particle will fall down before it can complete its circular path. The minimum value of Tr has to be 0 for the particle to complete the vertical circle. By taking Tr equal to 0 in equation 8 and solving it, we get v1 minimum is equal to square root 5 gr. That is, the minimum velocity at the lowest point in vertical circular motion is square root of 5 gr. Let this be equation 9. Using equation 4, the minimum velocity of the particle at the highest point r to complete the vertical circle is given by v1 square minimum is equal to v3 square minimum plus 2gr of 1 minus cos 180 degrees. At the highest point, the instantaneous velocity is v3, so v is replaced by v3 in equation 4. On solving this equation, we get v3 minimum is equal to square root gr. That is, the minimum velocity at the highest point in vertical circular motion is square root of gr. When a particle completes its motion along the vertical circular path, it is called looping the loop. Looping the loop is possible only when the particle has the minimum velocity of square root 5 gr at the lowest point. Thus, in our experiment with the bucket, if the starting speed of the bucket at the lowest point of its path is more than square root of 5 gr, then the water in the bucket will not spill out even when the bucket is upside down at its highest position along the vertical circle. On the other hand, if the starting speed at the lowest point of the vertical circular path is less than square root of 5 gr, the water will spill out when the bucket is upside down at the highest point of its circular path. You have now reached the end of this module. In this module, you learned that if a particle attached to a string is undergoing motion along a vertical circle, then tension in the string is a function of theta and the velocity of particle when the particle is in vertical circular motion. Tension in the string decreases as the particle moves from the lowest point to the highest point on the vertical circle. Tension in the string is maximum when the particle is at the lowest point, but it is minimum when the particle is at the highest point on the vertical circle. If the particle completes its motion along a vertical circular path, it is referred as looping the loop. Looping the loop is possible only when the particle has the minimum velocity of square root 5 gr at its lowest point along the vertical circular path. This minimum velocity of square root 5 gr is called critical velocity in vertical circular motion.